Good evening, everybody. Welcome to the third day of week 8 of our focus program on the Branges-Rovnyak spaces. We continue with the third lecture of Dan on HB spaces. Dan, please.
Thank you, Javad. So this is the third and last lecture, and I felt somehow that I have more freedom because in the first two I put subjects that somehow I felt should be covered if you want to make an introduction and to present the main features of these spaces. And here I just, I could choose some subjects in the area and elaborate a little bit on each of them. Okay, so the first subject is multipliers. Now, we already discussed that multipliers have this, well, in the general context of the producing kernel Hilbert spaces, have this property that you multiply and you get an element of the space. And the two properties that I discussed is that the operator is bounded and the norm is larger than the infinity norm, and then the supremum norm, which in this case means that the multipliers belong to H infinity. Now, in the case B is an inner function, in the case of model spaces, actually there are basically no multipliers, just the trivial ones. And the sketch of the proof, the reason is that you can just show a vector, namely S star U, that is in KU. This was shown by Stefan, but we also showed it for the case of B. But it's not constant, and it's if phi is not constant, then you multiply with phi and you get outside the space. It's if you want to see a very simple example, you just think of u z to the n, and you have the polynomials, and then z to the n minus 1. If you multiply it with whatever is not constant, then it gets out of the space. Okay, now what happens in our case? One moment, I just wanted to check something. Yeah, okay. So we have to discuss separately the two cases. First of all, the non-extreme case. We already know that if we multiply with a shift, then we remain in the space. So we already know a multiplier, namely SB, which is equal to MZ. But in fact, there are plenty of multipliers in this case. And we can deduce from this that if we take any holomorphic function on any function that is holomorphic on a whole neighborhood of the closed unit disk, then this function is a multiplier. And it's very simple to give the proof. We have already seen that the spectrum, although SB has norm larger than 1, the spectral radius is 1. So we may define a phi of SB as you want, either by the Ries-Danforth functional calculus, you take an integral around the spectrum, or maybe the simplest way is to do it by power series, and we obtain a bounded operator. And it's quite easy to check, for instance, especially for the with a power series approach, it's easy to check that it's precisely M phi. Okay, so we have a good deal of multipliers in this case. Now, in the extreme case, quite the opposite happens. So you look at point 2, if you have a non-constant multiplier, then it cannot be continued analytically across all of T. You see in the extreme case, all these functions that were homomorphic, or none of them can be except constant. Well, I won't prove this, but I will give just a an idea of the proof of the first thing, namely that if B is extreme but is not inner, then it has non-constant multipliers. And the construction is the following. We take the B that is not inner, and then it can be factorized by taking outside outer function that's non-constant, still contractive, non-constant, and with bounded inverse. You just look at the modulus on the boundary and you take somehow the larger part, you put only the larger part of the modulus and you take the outer function corresponding to it. And then it can be showed, but well, you have to work a little bit, that B1, this special non-constant function that's invertible in H infinity, is actually a multiplier. Okay, now, so we see that we have different possibilities here according to be extreme or non-extreme. So in the non-extreme case, we may ask ourselves this question: may we have the largest possible set of multipliers, that is H infinity? We know that, in fact, there are many analytic function spaces for which the multiplier are precisely H infinity. On the other hand, of course, in our case, for the extreme case, it cannot be true because of point 2 here. Well, actually, one can precisely characterize when the multipliers are the whole of H infinity. There's a whole list of properties. You can look, so here we have one that is our condition. We have condition 6 that we have already met in the context of invariant subspaces. But A and B form a corona pair, and this operator is invertible. And then I also commented that this condition of the operator is equivalent to the fact that the modulus of A squared has some nice properties, as is in the Helson-Segue, satisfy the Helson-Segue condition. And then we have a bunch of other conditions here, namely, well, H of B equal M of A is interesting, but maybe it's a little bit too technical. But the other three are quite easy to understand, namely that SB has these three properties that normally imply one the other. 2 implies 3 implies 4, but in this case, they are all satisfied precisely when this condition 6 is satisfied. You remember that I already discussed that SB is not a contraction. And one thing that I also did, I think in the first course, you see I had this nice example that I kept bringing it in discussion again and again, and it will appear today also. B of Z is equal 1 plus Z over 2. Well, in that case, I showed that that SB is not power bounded. If you remember, I just applied it to 1 and I get something that increases, that goes to infinity with n. And this is not surprising because if you remember, I also noticed that in that case, TA over A bar is not invertible, it's minus the shift. Okay, now I'm passing at something else. Commutants of some operators, some basic operators here. Or first of all, I discuss commutant of XB. XB is the most important operator on H of B. Sometimes it's the model space, the model operator when B is extreme, but anyway, it's quite important. And we know that it's invariant, that the H of B is invariant with respect to all T phi bar. with fine h infinity, I proved this immediately after discussing the sorry, after discussing h of b. And if we make the restriction, then the operator is bounded. And of course, it commutes with with xb, which is tz. In fact, all these operators commute. They form a commutative algebra because they are the restriction of commuting operators. So the commutant of xb contains all these operators. And now there is the natural question whether any operator commuting with xb is of this form, whether this is the description of all operators in the commutant. Well, this is true if b is non-extreme, namely an operator commutes with xb precisely when there exists a function phi such that a is t phi bar restricted to h of b. However, in the extreme case, it's a little bit more complicated. Namely, this equivalence is true precisely when b is inner. For inner function, it's probably not too complicated to prove it, but then it follows, there's an old result of Nog and Foyash that says that if b is extreme but non-inner, then you have other operators in the commutant. Well, now, as we did in yesterday's course, xb is an operator that we can discuss, that we in both cases, extreme and non-extreme. While in the non-extreme case, there is also a natural operator to consider, namely SB, which is the restriction of the shift operator on the space. So in this case, all multipliers, m of h of b is commutative always, and SB is the multiplier corresponding to z, then of course all multipliers are contained in the commutant. Well, actually, the converse is true also. So in this case, you have this nice result that the multiplier algebra of SB is precisely the same as the commutant algebra of SB is precisely the algebra of multipliers. Okay, well, now I want to discuss a particular case of H of B space. So up to now we had, today we had some general abstract situations, but it's an interesting example is to see what happens if B is rational. Now, in case B is rational and extreme, then things are quite trivial. Well, not trivial, but they reduce themselves to model spaces because a rational extreme function is inner. It's a finite Blaschke product, and we know lots of things about these spaces. So we have to consider B non-extreme, and we know that in this case, B rational implies A rational. Okay, what happens with H of B in this case? Remember then the example I told you that this keeps reappearing, 1 plus z over 2. So in that case, we had a concrete description of H of B. It was the constant, the complex number, direct sum with z minus 1 h2, and the norm was the natural norm of the direct sum with the, but we had to take care that in the right-hand side, we have to take the norm of f, not the norm of z minus 1f. So the idea was would be to find a similar result for a general non-extreme rational function. This is a non-extreme rational function. Well, such a result exists. It's a theorem obtained by Kostara and Ransford in 2013. And it is the following. We have a rational non-extreme B. Now to B, you have associated its mate A. Now you look at A and you're interested in the zeros of A on the unit circle. It cannot have zeros in the disk because it's outer, but it may have zeros on the unit circle, and they may have different multiplicities because this does not prevent A to be outer. Well, so I denote the zeros by zeta j and the multiplicities by mj. And then we have a similar formula to the one that we had here for the case 1 plus z over 2. As a set, yeah, so sorry, there's an h2 missing after this product at the beginning. I can try actually to write it. I hope that, let me see. This would be nice if I can do it. Okay, that's fine. Plus Pn minus 1, where Pn denotes the vector space of analytic polynomials of degree at most. Well, of course, Pn at most n and Pn minus 1 at most n minus 1. So in the previous case, you had B has degree. In fact, it's not B, it's A, which is 1 minus z over 2. So it has a 0, 1, and you have the degree 1. And so you have to put only the constant here. Well, this is as a set, but not only is it as a set equal to this, but also the two terms in the right-hand side are both closed and their intersection is 0. So this is an algebraic direct sum. Well, it's not only algebraic because the spaces are closed. And once we have such a decomposition, the norm is equivalent to the norm taking that we may have considering the two parts. This here in the first part, we have the norm of G, and in the second, you have the usual norm of P. Now, anyway, these are equivalent norms, so you can take any norm for P, which is finite dimensional. You have to take the norm, the H2 norm of G, but then, of course, the norm is also equivalent to square root of norm of G squared plus norm of P squared. Okay. So let's give a sketch of the construction. First of all, since B is non-extreme, we already know that all polynomials belong to H of B, and in particular, Pn minus 1 belongs to H of B. Now, this is what we have to be a little careful, namely to show that for any of the zeros of A on the unit circle, all functions in H of B have non-tangential limits, and not only they have non-tangential limits themselves, but their first mj minus 1 derivatives have non-tangential limits, where mj, of course, is the multiplicity of the 0 zeta j. Well, so once we know this, so we know that we can define the value of the function of the value of f and of certain of its derivatives in the points zeta j. We just interpolate these values by a polynomial, and then the difference one can see easily that is exactly in the space z minus the product z minus zeta j mj h2. And of course, you have to be careful to prove also the thing with the norm, but this is the idea of the construction. And I just warn you that the decomposition is not in general orthogonal. In that simple case of z plus 1 over 2, it was orthogonal, but in general, it's not orthogonal. Okay, so what happens with the okay, so one problem that we can easily solve is what happens with the multipliers in this case. We know that in the general non-extreme B, the multipliers are contained in H of B intersected with H infinity. But in fact, in this case, we can show that it is equal. And this is a result by Friquin, Hackman, Ross 2 years ago. So the multiplier algebra is equal to the intersection of these algebras. And the proof is quite simple. We may do it now. If we denote the product that appeared in that form, that representation of the H of B space by alpha of Z, then we take phi. So anyway, we know that multipliers are contained here. What we have to do is to prove the inverse inclusion. So we take a phi in the right-hand side here, and an f in H of B, and we have to show that the product is in H of B again. So we write phi and f according to the decomposition. Then we multiply, and then we take alpha as a factor wherever we are able to do it. So we can do it in 3 of the 4 terms, and then we are left with PQ. But then it's easy to see that since alpha phi tilde is phi minus p, it is in H infinity because phi was in H infinity. Then f tilde is in H2, the product is in H2. So the first term here is in H2. Then the two next ones are immediately in H2 because they are functions in H2 multiplied with polynomials. And in the end, so this means that the first term here is in alpha H2, which is contained in H of B. Now, for the second, it's simple because it's a polynomial. So we make the division by alpha. We have a part that is in alpha H2, in fact, in alpha times polynomials, plus Pn minus 1. And the result is in H of B. Okay, so we also know the multipliers for this example. We know much about this space, but there is even more that I will tell you soon, but maybe not immediately, because now I come back to some more general stuff about these spaces, namely integral representation. So again, we're starting from the model spaces KU. And remember that there were something that were called Clark measures. They were singular measures defined on the circle, and they came together with an operator that intertwined multiplication with a variable on L2 of the measure with a one-dimensional unitary perturbation of the model operator. Well, if you don't remember it, there's no problem, because anyway, we will do this for the Branges-Rovnyak spaces. But let's write some definitions. We take a complex Borel measure on T, then H2 of mu is the closure of the polynomials, and the Cauchy integral of mu is defined by the usual formula. Okay, now we take our B in the unit ball of H infinity. Now there's no assumption about extreme or non-extreme. And it's easy to check that the real part of this fraction is positive. So it's the Poisson integral of a positive measure. And this is called a Clark measure for the moment. Actually, there's a whole family, but we will come back to this at the end. For the moment, it's just this one. And then we define this operator on L2 of mu b by this formula. We take the Cauchy transform and then we multiply it by 1 minus b of z. Now, what happens here is that we can, if we compute, we find out that if we apply VB to the Cauchy kernels in the first space in L2, we get this formula. And the scalar product of two Cauchy kernels with respect to mu is precisely equal to the scalar product of their images through VB. So since we have in the left-hand side a total set in H2 of mu, in the right-hand side a total set in H of B, we immediately obtain that VB is a unitary operator between this space and our H of B. So we can translate, well, sometimes we can prove properties in H of B by translating them through VB on things that happen in H2 of mu B, which is presumably more easy to understand. For instance, I give you an example. If we take a multiplier in M in H of B, then one can show that if we go through VB, so, well, the operator M phi star acts on H of B. Now, if you see this product of three operators, is that we have transported M phi star in H2 of mu B, and it can be shown that this coincides on function in the disk algebra precisely with T phi bar. So one consequence that we can deduce from here is that there is a way of seeing whether this phi is a multiplier by checking what happens with T phi bar in the disk algebra, whether it's bounded in the norm on L2 of mu B. Okay, so in fact, I was telling you that usually one speaks about the Clark measures as a plural. And the reason is that H of B is the same as H of lambda B for modulus of lambda equal 1, but the measures are not the same. The measures are different. And many results are stated concerning this whole class. And I give you two examples here. If we have B, a function in the unit ball and the point, zeta in T, then the condition that B has an angular derivative in the sense of Kara-Theodori that has already appeared at some point in the first course is equivalent to the existence of lambda in the circle such that mu of lambda B has an atom at zeta. Another example, well, if B is non-extreme, or even if B of modulus of B of zeta is smaller than 1 almost everywhere, then this measure, we cannot say, if we take just mu1, we cannot say that mu1 is absolutely continuous. But we can show, if we look at the whole class of measures, that most of them, in the sense almost all of them, are absolutely continuous. Okay, so I'm finished with this subject, but it can be much extended. So this using Clark measures is a very efficient tool to do different things with the Branges-Rovnyak spaces. Okay, so we come at contractive embeddings. For model spaces, if we ask ourselves when two model spaces are contained one in another, it's very simple to give the answer if and only if the function u2 divides u1. What happens for H of B's? Now here there is, we have to be more clear about what we mean here, because for the model spaces we have the same norm. So what happens? Inclusion is clear. There's a unique sense in which we can speak about inclusion. But here we have different norms. So we can ask ourselves whether they are included the same norm, or rather, maybe this is too strong when they are contractively included, or when they are included as sets. And the first question that I state here is this one, because it has a very similar answer. H of B2 is contractively included in H of B1 if and only if we have a factorization. So you can say with B in the closed unit ball. So you can say that B2 divides B1, but B has also to be to be in the unit ball. And the two spaces are the B's differ by constant, by unimodular constant, which actually we just used in terms of Clark measures. So, for instance, one can show that all these H's are included one in another, but moreover, we can show that the inclusions are all strict. Okay, now if we don't ask for the contractivity, the condition, the situation is quite different. As I said, in model spaces, we don't meet this problem because the norm is anyway the same, it's the norm of H2. But here, if we ask just for inclusion, it becomes more complicated, and you can think that it's not so simple if you remember that whenever B has infinite norm strictly smaller than 1, then H of B is actually H2, but it's a renormed version. One theorem that we can prove that if we have such an inclusion as sets B2 extreme implies B, non-extreme implies B1 non-extreme. And then we have a general theorem that tells us when we have inclusion as sets, but which is a little bit more complicated, that as you can expect, that just division. Namely, if we have two functions in the closed unit ball, then H of B2 is contained in H of B1, if and only if, now you see we have to have two VW in H infinity and the constant gamma such that these two conditions are satisfied. So it's a little bit complicated. From condition 2, actually, follows the theorem before, because you have, if the integral of the non-extreme and extreme are determined by what happens with the integral of such a quantity. And then from this inequality, you can obtain that B2 non-extreme implies B1 non-extreme. But if you want, as I said, if you want to have to characterize the inclusion, it's more complicated. Okay, now, sorry. I'm sorry, Javad. The microphone is on the laptop on the left-hand side, and sometimes I move my hand and touch. Okay. Yeah. So we'll see now. Okay. Yeah. We want to discuss now another way of another case when H of B spaces can be described in a different manner. And these are Dirichlet type spaces that have already appeared in one of the talks in the last 2 days. Now, remember that the norm on the usual Dirichlet space is given by the sum of the H2 norm plus the integral of the derivative squared. And suppose that we change the second integral by introducing the Poisson kernel here as a weight. Well, in this case, actually, there is an alternate way of calculating the integrals in terms of values on the boundary. So here on the left-hand side, you have an integral on the disk. On the right-hand side, you have an integral on the circle. Now, on the disk, there's no problem to consider f of z, but on the circle, of course, f of 1, it might not mean something. So to make sense out of this, I have to state it more clearly in this way. These two things are equivalent. The first integral is finite, if and only if the second integral, that f has the non-tangential limit in 1, and then we can write the second integral. And in this case, the integrals are equal. Okay, now there's a theorem obtained by Richter and Sundberg in 1991 that says that, again, our old friend b of z 1 plus z has the property that the Branges-Rovnyak space is precisely equal to d1, to this d1, with equivalent norms. And the proof is, in fact, in this context, they proved more in that paper, but in this context, it's not very complicated. We know that if f is in d1, f has radial limit in 1, and then this is what I said before, and g is in h2. You see here. Here is exactly this thing that g is in h2. So f of z can be written f of 1 plus z minus 1g, and from here it follows that f belongs to h of b. Conversely, if f of this form, then we can reverse the argument. We know that in this case g has limit in 1 and g is in h2. So in some sense, it's just writing things in different ways. So this h of b actually is the same as d1, and the advantage is that you have an integral. You can define it, the norm, by a clear integral, and in fact here you can deduce the scalar product, and it's not so elusive as it used to be when I looked at it only as the Branges-Rovnyak space. And in fact, you can extend this, you can generalize this argument. You take for mu a positive measure on the circle, you define the local Dirichlet space to consist of the function for which this integral is finite. Here is the Poisson transform of mu. So you have, instead of taking here 1 as in the usual Dirichlet space, you have put a weight here, the Poisson transform of mu. And then this becomes a Hilbert space with this norm. You always have to add the usual norm of f, because f prime of z gives norm 0 on the constant, so you would get a semi-norm. And there's a theorem of Costara and Ransford that says that in the case that mu is a finite linear combination of point measures, then there exists a non-extreme rational b such that d mu is equal to h of b with equivalent norms. Now, the general problem would be to characterize all the mu's for which we have d mu equal to h of b, or all the b's for which there is some d mu, but in general, we don't have such a general result. We know just necessary and sufficient condition to have such an equality. The sufficient was given before, that we have a finite sum of point measures. Now, here I said with equivalent norms, and I want to also to state well, a kind of curious situation that if you require equality of norms, then there is essentially a single possibility for d mu equal h of b. Mu has to be the multiple of a point measure, and b has this form which, okay, so there you can vary some constant. It's a single type of function if you want to have equality of norms. Okay, let's pass to something else to connect the Branges-Rovnyak spaces with interpolation. So the Nevanlina peak problem for reproducing kernel Hilbert space is this one. When, if you are given points in D and values in C, when you can find a multiplier of norm smaller than 1, which takes precisely those values. And this is a, well, I enter a little bit in an area that is very much studied. I just tell you a few things that I need here. Since we remember that we had a condition, a general condition for RKHS for a multiplier to be to have norm smaller than 1, namely that this function has to be positive definite. It means that this matrix must be positive semi-definite, because this is precisely the matrix that I obtain if I take here phi of zi is lambda I. Okay, and of course we can extend, and there is a reason to extend this to a matrix valued multiplier. We obtain that the similar condition is that this must be positive semi-definite. This is, I'm getting a little bit outside our context, but the reason that I did this is that this defines what is called a complete Nevanlina peak kernel, a kernel space in which this necessary condition is also sufficient. And these kernels are very precisely defined by Egler and McCarthy, and it's not surprising that, again, the condition is that some function should be positive definite. And you have some examples: Hardy space, Dirichlet space, Drury-Arveson space. I think these spaces will be discussed in a course later on. Now, my problem here is, when does H of B have the complete Nevanlina peak property? Because I'm interested in the Branges-Rovnyak spaces. Well, first of all, it's easy to see that Ku has the complete Nevanlina peak property if and only if it is one dimension. So the model spaces usually do not have the Nevanlina peak property. But there are the Branges-Rovnyak spaces that have the complete Nevanlina peak property. And there's quite a little surprising result given by Chu in 2020. The paper was published in 2020, but it did circulate before. So the result is the following. If you take H of B, it has the complete Nevanlina peak property if and only if, now this is quite a cryptic condition, I would say. So B has to have a left inverse with respect to composition on D. And moreover, you must have this condition for the function z minus b of 0 over h. Now, I can't say you too much about the proof and about what this happens, but I will give you some examples. Well, of course, I start again with 1 plus z over 2, because this is what this is my favorite example. And in this case, I can take h of z to z minus 1, and it's very easy to check the two conditions before, 1 and 2. So indeed, the space h of 1 plus z over 2, sorry, I So the H of my H of B space that I got so fond of and I showed you a lot of properties about, indeed has also the Navanian peak property. You can generalize this to very simple rational functions, for instance, functions of the type z plus a over b, but you can also get more complicated examples. If you take a simply connected domain larger than the disk, and phi would be the Riemann mapping from this domain to D, and B, its restriction to D, which of course is in the unit ball of H infinity, then H of B has the complete Navanian peak property. Now, phi is quite clear that we will take H to the -1 because it has to be a left inverse. And in particular, this is interesting because if I'm careful to ensure that the boundary of omega contains an arc of the unit circle. Let me just, okay. So we have the unit circle. And omega, let's suppose that it's something like this, contains this arc, and then it's something larger. Well, then we obtain an extreme B. So not only, like you might think, only non-extreme B can be obtained. Okay. Now there are, I think this is the last thing that I will do. H of B may be characterized as subspaces of H2 in the sense that you are looking at a subspace of H2. And well, when is it a Hilbert space contained in H2? When is it equal to some H of B? And there is a characterization. The non-extreme case, I start with a non-extreme case, which is a little bit more complicated. And it was shown by Geiger in 1991. Of course, there is, you have to put out from the beginning the condition that the space has to be invariant with respect to S star. And then it's equal to H of B for some non-extreme function B, if and only if these conditions hold. Now, the first two, maybe you remember them. They appeared also in the abstract characterization of operators that are unitary equivalent to some S star restricting to the Branch spaces. The second and the third, they are quite, well, let's say common, well-known conditions that appear in the Branges-Rovnyak, well-known properties of the Branges-Rovnyak spaces. We haven't met them, but they are quite familiar to people working. We have the inequality for difference quotients in general. And moreover, there is an element for which we have equality. Okay. So I can just tell you that if one is satisfied that the element in 3, for the element of 3, you can put this formula. The extreme case, it's simpler to characterize. In fact, it was already done by the Branges and Rovnyak in 1966 in those two papers. Namely, you have to ask that this defect has rank 1. And moreover, you have equality for different quotients for any F in the space. So in particular, KU satisfies this. For instance, the equality is clear from the, if you look how acts the adjoint of the shift, it just cuts the first coefficient if you look at the norm. Okay, now there are other, I put just a list to tell you that there are lots of subjects that I have not touched at all, like, well, this is a kind of making the subject a little more exciting. in many of these areas, there are still open problems. Like, well, Carlson and inverse Carlson, Clark measures, relation to other problems, composition operators, Bernstein inequalities. And the last point actually can be a big area of study to see what you can extend to them. Okay, thank you.
Thank you indeed. Let's then wonderful series of lectures. Any question or comments for them? There is a question in the chat.
Conjecture for the set of multipliers. What is this set? Let me come back then to. Oops. Yeah. So a description of all multipliers. This is what well, I don't know. I don't think there exists a clear description of all multipliers. So these are necessary or sufficient conditions, but I don't think that in the general case, of course, if in some cases, like, well, for the model spaces, you know, it's very simple that there are no multipliers, but otherwise, I don't think there is a characterization of multipliers. Well, there was one by going to the Clark representation, but it's not necessary. Can we hold the same?
And I remember vaguely, there is a paper, a long paper by Ben Lotto and Sarason about multipliers. But I don't remember what the results are. It's just.
Yes. Well, this is one of the first papers, I think, in the area. But I don't think there is a.
No. It's not no characterization, but it's a long paper with might have interesting results.
Mm-hmm. And there is the question whether we can hope the same result as for rational function. I think no. I mean, if you think that multipliers should be H infinity intersected with the space, I think there is a counterexample. This is clear. Manu, maybe you know the exact reference, but I remember that.
Yes, I think this is a result of in the paper of Lotto and Sarason. Well, in fact, they prove that H of B intersect. They have an example where they prove that the intersection of HB with H infinity is not an algebra, so it cannot be the multiplier set.
Mm-hmm.
Any further comments or questions for Dane? If not, let's thank him again.
Okay, I stop sharing that.